Hi, I'm Richard from Off Grid Common Sense. Today I'll be showing you my DIY hybrid wind and power system. Before we get started, a quick disclaimer. I built this system myself, so I am responsible for my own safety. If you are building your own power system, after watching this video, you are responsible for your own safety. I will not be held accountable. Please do it under the supervision of a qualified electrician. Approximately 7 years ago, I started building my power system because I had an interest in solar power. I wanted to build a small portable backup system for emergency use. Over the years, the system has grown and is no longer portable, and I also recently added a wind generator. I've used this system a few times during short power outages, and it was extremely handy to have. Now I'd like to take you outside and show you my solar panels and wind generator. Then I'll show you my battery bank and the control setup that I keep in my garage. After that, we'll come back inside and I will use this whiteboard that is behind me to draw out how my system is connected and the settings my controls are at to keep my batteries full and how I use the excess power in my home. So here we are outside looking at my solar panels. On the left, you can see the panel is different than the rest. This is a factory-made solar panel. This one happens to be a 100-watt panel at 12 volts. I have seen it put out a maximum of 6 amps in my location. All of these other 4 panels are home-built panels. The most I have ever seen these put out is 2.5 amps, which equals about a 30-watt panel total. This one's 100 on the left. All these other ones are 30. I built these homemade panels because I thought it would be fun, I thought it'd be cheaper, and I thought I would get more power out of them. And I do not. I don't recommend wasting the time building your own panels. It seems cheaper when you look at pricing, but when you factor in how much time it takes and the low output that you get, I don't recommend doing it. But I will put a link in the description to my Instructables page that I made several years ago about how I built these panels. Again, I don't recommend you waste your time doing it. Buy factory-made panels. They put more out, they will last longer, and you can see how much space that left factory panel takes up. And I get it's a 100-watt panel compared to all these other panels, which total 30 watts. I could easily put 3, almost 4 factory panels in the space that my homemade DIY panels take up. So if you look up above my solar panels, I have a 5-blade 1200 watt wind generator. It is mounted on a 1.25 inch black pipe. It is about 20 feet off the ground, which may not be as high as you would like it to be. Seeing as this is the first wind generator I've ever used, I put it at a relatively low height just because if I need to work on it, it would be easy to access. It is rated at 1200 watts. What that 1200 watts really means is 1200 watts over an entire day. If we had a steady wind, this wind generator could put out 4 amps for 24 hours, and that at 12 volts, and that would equal 1200 total watts for the day, not 1200 watts at one time. The most I've ever seen it put out was 6 amps during a storm. It only peaked at that quickly and then the controller disconnected. This wind generator came with a small controller that takes the 3-phase AC that is put out by the generator head and converts it down to 12 volt DC. The most I ever seen it put out is 3 amps continuously for any amount of time. If it gets too low, the controller turns off, and if it goes too high, the controller will disconnect and actually feeds back the power it's producing to slow it down. It's a safety feature of the controller. I don't really like this controller. I think there's a lot of waste in it, but it's the one that came with it, and I don't want to buy a new controller at this time, so I use what came with it. One thing I didn't realize about even these small wind generators, is they are much more noisy than expected. I didn't think a small generator like this would produce hardly any noise, but on a windy day you do hear it wind up and wind down from this side of the house. When it's a windy day and you'll hear a whistling noise. Again, I didn't expect it to be as noisy as it is. Just be aware. So here we are at the back of the building, and I wanted to show this junction box. On the left side of the box, the wires that are pulled out, those are all of my lines from my solar panels. Each panel has its own connection down here. Above this J box, you can see there are those red blocks and a black one. Those are automotive fuse holders. Each panel has its own fuse in line just to protect everything, protect the panel and protect the entire system. They all come inside this box and connect together, and then they run down the back of the building through a small trench to my garage where they connect to the actual battery system. This green box that is in the upper right hand corner is the actual charge controller for the windmill. The blue lines coming out of the box are the three-phase AC coming from the wind generator, and then there's red and black on the right side. That's the 12-volt out. Now here on the back side, I wanted to explain how I adjust my panels. The center board that is under these solar panels is actually screwed to a set of hinges. Those hinges are also screwed into the rafters of the building. This allows for me to adjust the panels with this 2x4 that is hanging down. This 2x4 that is hanging down, at the top you can see a shiny spot, and that is another hinge. That allows me to adjust these panels without putting any kind of bind into the frame, and it smoothly adjusts. Coming down to the bottom of the 2x4, there are 3 holes. These 3 holes are to adjust my panels for the summer when the sun is in the highest point in the sky, the winter when it is in the lowest point in the sky, and the fall and spring when the sun is somewhere between the high and low. I put a carriage bolt through a stud on the inside of this building and a washer and nut to hold it to the building. And then I put the 2x4 over that carriage bolt and another washer and nut to hold it in place. When I need to adjust my panels for the time of the season, I just simply use a wrench to take off the nut that you can see in the washer and move up or down to the appropriate hole for the angle I need for that time of the year. I put the nut back on, tighten it down, and it stays in place. Here at the bottom of my wind generator is maybe difficult to see, but there are 2 eye bolts that go through the building, one on each side of the pipe. Through the pipe is a 1/2-inch bolt that goes through both eye bolts. It basically makes it a hinge, and it also keeps the pipe from being able to spin. At the top, I did the same thing, but the bolt does not go through the pipe, it just goes on the outside of the pipe. If I ever need to lower this wind generator to work on it, I can tie a rope to it, go to the other side of the building, take out the bolt, and then I can use the rope to lower it down since the bottom point is a hinge. This way it doesn't fall down, it doesn't twist on me, it doesn't do anything. I can lower it down easily by taking out the bolt and using a rope. Well, now that I've shown you what is all on the outside, my solar panels, my wind generator, how my solar panels are adjusted, and that junction box, now I'll go inside to my garage and I'll show you where the other end of this cable feeds into my controls and my battery bank. Here we are in my garage, and this box contains all of my controls and my batteries. Originally, when I started building this system 7 years ago, I wanted it to be portable. So I put everything in this box, except for the solar panels I had outside at the time. I have since outgrown being portable. It is now very stationary. In the bottom of this box are 4 batteries, and it is too heavy for any 1 or even 2 people to pick up. On the front, first I want to explain what all these meters are. The one on the left that is currently saying 6.9 is input amperage from my solar panels only. This does not include what is being put in when the wind generator kicks in. The highest I've ever seen this meter is 8.5 on a really clear sunny day. To the right, there's an orange block that was the meter for voltage in and has since quit working. I have not replaced it because I want to completely redo all of these controls on a board that mounts up on the wall so I can get my floor space back in my garage. In the center underneath the latch is a meter like you find on like golf cart type equipment. It gives a empty to full reading, almost like a fuel gauge, of your battery state. You can look at it quick and know approximately how much power you have in your batteries. To the right, the meter that says 00, that is amperage out. Currently I'm not using anything on this box, that's why it says 0. The next one to the right says 12.5 currently. That is the battery voltage at this moment. It bounces from 3.8 to 12.4, 12.3. We're back inside later on. I will explain why it does that. Looking to the left of my box, you can see a black cable coming through the wall. That cable is the other end of the cable that I set outside was in the J box that ran down and through a trench to my house. That is where it comes in. And on the floor over here on the right side is a white meter. That is the power I am actually putting back into my house, and I again will explain that better later on. Here in the lid I mounted a thermostat. Normally the box is closed, and since heat rises, I put the thermostat in the lid. This thermostat controls this row of fans along the back. These are just old DC fans I took out of some old VFD units that died. There are a lot of leakage holes around this box for airflow for these fans if needed. I don't think they've ever actually kicked on. With this sitting in my garage, it's always been in a shady area, even in the summertime. It's never gotten to a dangerous heat level, but it is a safety feature that I put in my box. So down here on this white plate are where all of my controls are. Starting over here, this is my solar controller. This is what takes all the wattage from the solar panels and it gives it to the batteries in a charging current. This also controls power from the batteries out to other devices. This is a necessary controller for anybody that's using solar panels. You must have solar panels, a controller like this, and a battery at minimum. Again, you can see these black blocks on yellow wires. These are automotive style fuse holders. Again, I like to have lots of fuses, lots of safety built into my system to protect everything. They're very messy. As you can see, there's lots of wires hanging out and I really don't like it, but they are cheap and easy to get, and fuses are fairly cheap to replacing them. At some point, I'm going to rebuild this in a stationary wall mount unit. You can see I have terminal strips here, and I have a row of terminal strips in this corner. I'm not going to go through what each one is, but it is all of my connections. I made it easy and simple to connect and disconnect things by using these fairly inexpensive terminal strips. Down here you can see these two black and silver units. These are amperage shunts. These are what measure amperage going through my lines and deliver that reading to the meters on the front of the box that we talked about earlier. This circuit board over here is a special circuit board. What it does is it measures the battery voltage at all times, and it has two settings, a high setting and a low setting. The high setting turns on an output and the low setting turns off an output. In my case, my output is this relay over here. Again, this is a automotive relay, cheap and easy to get. Later on inside on the whiteboard, I will draw out exactly how that's connected and why I put that in there. But for now, you can at least see where it's at. This black unit in the front, many of you may recognize, it's an old UPS unit. Several years ago, the battery that was inside of it died. So I took the battery out and I hooked up my 12 volt to it from my batteries, and this is what provides my 120 volts when I need it. This big silver unit that says power inverter is a grid tied inverter. What it does is it takes 12 volt DC and converts it to 120 volt AC. These particular units actually take whatever power they're given and push it back into your house. These are not a typical inverter that you just plug into and use power from. This particular unit has a safety feature inside of it. It looks to see if there's 120 volts in the receptacle it's plugged into available. Every, I think, 2 to 3 minutes, it looks for this. If there's power available, it will push power out that it's given. If it sees there's no power available, it goes into a standby mode. This way, if the grid system is down, I am not pushing power back out into the grid from this little inverter. Again, inside I'll explain why I use this, because at this point most people would use a typical heater coil. I decided to go this route, and I'll explain more why later. Underneath this white plate are my batteries. You can see that I have 4 EverStart deep cycle marine batteries. There's a lot of arguments on what batteries to use in a solar system. These are the ones I chose because they're easy to get and I could afford them. These 4 batteries are 12 volts and they are connected in parallel. So my entire system is a 12 volt system. This is the right side of my controls box. I wanted to show you how I can actually access the box without having it open. Down here it says USB power. I turn this on when I actually want USB power out of my box. If you look under this flap, you'll see there are 2 standard USB plugs. They're only on when this light's on. Otherwise it would drain power constantly and I'm not using it, so it's wasteful. Next to that is a standard 12 volt outlet like you'd have in your car. Older people of us would call this a cigarette plug. Younger people will call this an accessory port. But it's 12 volts all the time. I can plug anything in that's a 12 volt source that uses this type of connector. These solar inputs here are screw terminals. When my old system only had a few panels that sit in the yard, these were the connections I had to my panel. Now that my panels are mounted permanently on top of a building, I'm not using these inputs anymore. It runs straight into a terminal strip from the cable that's from outside. As we move over, you can see these say 120 AC. These are just a standard receptacle like you have in your house. This is where I get my 120, again, without having to have the box open. I wanted to show you a better close-up of this watt meter. The big number in the middle that says 105, 104 right now is the actual wattage that grid tie inverter on the inside of the box is putting out and pushing back to my house. The number at the bottom, the 56.50, this is the approximate amount of money that I have saved from my solar panels and my wind generator pushing power back through that grid tie inverter and back into my house. The number at the top is just time and military time. These watt meters are fairly inexpensive. They give you a lot of good information. To get that 56.51 at the bottom, you enter in the cost of your electrical wattage usage that the electric company charges you, and it will multiply that by how many watts have gone through this meter. It gives you a quick estimate of how much money you should be saving. Now that I've given you a quick overview of my controls and my batteries, we'll go inside and on a whiteboard I will draw out how the system actually connected. So now we're back inside. On the left half of this whiteboard, I'm going to draw out how my power system is connected. It's a simplified version. I'm not showing every positive and negative line. It's just how things are connected. So here in the center is our battery. I'll start up here in the corner. This would be all of my solar panels I have out in my building. You need a solar controller to handle the power from your solar panels coming in, and then it connects to the battery bank and charges the battery. This controller has another line for out. This line out is where power from your battery bank comes back through the controller and is fed out to any devices that you have connected to it. This would be lights, inverters, whatever you can use the 12 volts for. We'll come back to that in a moment. Over here we have my wind power, which comes down and it has its own controls, and it also feeds the battery bank separately. From the battery bank, I have connected my inverter. This inverter does not run through any other controls, because if it was an emergency and I was using this system as a backup, I want to make sure I have the full volume of my battery bank available to my inverter, which makes it my responsibility to make sure my battery bank is not drained too far and damages the batteries. Now at this point, many people also add in what they call a dump controller. This takes power from your battery bank and runs it to heater coils. The reason they use these heater coils is because they're not tied to the grid. All of this power coming into your battery bank needs someplace to go. If you are not grid tied like I am, and if you are not using this battery bank and your batteries are full, you don't want to overcharge them. So what they do is they put in this dump controller, which sees when this battery bank goes over the desired setting for safety, and it just dumps all the power to these heaters. These heaters just convert all the power coming in into heat and burn off the excess power. And then when the battery bank drops down to where you want it to be, the dump controller turns off. To me, it's a very wasteful system, but it's a necessary component if you are not grid tied. In my case, I am grid tied, so I do not have a dump controller and a heater unit. What I do to take up this excess power coming into my battery bank is I run this outline over here to my grid tied inverter. This grid tie inverter then plugs into my wall like any other device. As I said before, this grid tie inverter takes the 12 volts DC, converts it to 120 AC, and actually pushes it back out. But if I have it hooked up the way I show here, this solar controller will allow this grid tie inverter to drain the battery bank to empty. And I don't want to do that. I don't want to drain my battery bank to empty, have this turn off, wait for my batteries to charge up, turn this back on, where it starts that cycle over again. I want to only dump my excess power to this grid tie inverter. The way I do this is I have another small control board connected to my battery bank. It watches the voltage in my battery bank to tell me when it's high, when it's low, when it's empty, when it's full. And in this line, I put a relay. This unit controls this relay to turn this power to my grid tie inverter on and off. So the solar controller allows power out to the relay, and this relay controls the power to my grid tie inverter dependent on the control settings I put in the small control board. That's the basics of how the power is handled in my system. Now there's a few other things that I showed you earlier, the different meters. I'll show you where these are at. So this is my voltage in from my solar panels. I also have the amperage in from my solar panels. At the time I put these in, I did not have wind power. That's why none of my wind power incoming voltage goes through any meters. Later on, I would really like to upgrade my entire system, add more measurements where all of these things will be on meters and I can tell much more in depth what is going on in my system. This was one of the shunts I talked about earlier, and this is a second one out here, and this is the amperage out meter that was on the front to know how much amperage is leaving my battery bank going to my inverter when I'm using it. So I can meter this meter, and I can balance how much I'm using at the time to make sure I can put in enough to compensate for what I'm taking out and attempt to keep my batteries full when I'm using this box. There were two other meters. This one, which had the small lines in it, I said it was like a golf cart type meter, battery meter. Just a quick visual representation of empty to full, like almost like a gas meter or a gas gauge in your car. And then there was also another digital one for the battery current voltage. Two ways to know how much power is in my battery currently. And I used this meter when I was setting up this control board to know when it was turning on and off. Now over here on this right side, I am going to graph out how my battery voltage is controlled to make sure this battery bank is full and what is being sent to this grid tie inverter as excess power that I'm converting back into my house. So this axis will be voltage, and this bottom axis is time. This is not a standard time, it's just general in time. I have 11.2 volts. For deep cycle marine batteries, 11.2 volts is considered an empty battery. You never want to get your batteries to that point. This is 12.6 volts. This is what's considered a full battery. If you buy a brand new battery off the shelf, it should be in the vicinity of 11.6 volts. That's what's considered a full battery. Up here at the top, we have a few others. We have 13.8 and 14.8. and 14.8. The 13.8 is considered a float, which means it's okay to keep your batteries there for long periods of time and it will not cause damage. If you continue over the 14.8 and you get up close to 15 or more, this is where you can actually damage your battery and you might even see the case swell. At that point, that battery is not any good. You would need to replace it. So the way the solar control over here works, if the voltage is below 11.2, it does not turn on this output line. It waits until the voltage hits this 12.6. If it drops back down to 11.2, the solar controller will turn off and wait for it to come back to 12.6 and then turns back on. If the voltage continues higher, and it will allow it to get to this 14.8, this is where it actually disconnects the incoming power from your solar panels. So it keeps your battery bank up here in this 14.8 area and waits until it would drop all the way back down to 11.2 to turn off. Once it drops below 14.8, it will reconnect your solar input until you go back over this. It'll just sit here and bounce if you're not using your batteries. Well, in my case, I don't want to wait for my batteries to be dead because I was running to a grid tie inverter and wait for them to come all the way back up to full and then go back to dead and full. This will extremely damage your battery in a very short amount of time. That's where this other control board that I added and a relay comes in. I don't want to drain my battery bank below the 95%. It's for emergency backup. I want to make sure my bank's always full and ready to use when I need it. So this little control board watches the batteries. When this board sees the 13.8 volts, it turns on this relay, which means all the power that is in either my battery bank and my incoming from my solar and wind is allowed to go to my grid tie inverter. This is the on point. It will wait until the battery voltage drops to 12.4 volts. And turns off this relay, stopping the grid tie inverter. The reason I set it for this band is you can run these batteries in the 13.8 up to 13.8 safely and down to 12.6, which would be full. So what I wanted to do was take all of this excess energy between 13.8 and use it till it hit 12.6 and send it to my grid tie inverter to send it back into my house. The problem I ran into is when I set it for 12.6, as soon as this would turn off, this would start shooting right back up. It would hit that 13.8 and it would drop it very quickly back to 12.6 because this is just the excess coming in off your solar and wind inputs. Depending on the day, if it's a very sunny day, I could make this jump very quickly. And what would happen is this grid tie inverter would only be on for maybe 20 to 30 seconds when it hit the 13.8 and it would drop to the 12.6. Then it would turn back on maybe a minute later and it was only on for less than a minute and it would drop. So it would be short cycling. That is extremely hard on these grid tie inverters. You want to either leave them on or leave them off for an amount of time. So what I eventually had to do is adjust the settings, the on settings, on this little control board down to about 12.4. 12.4 still leaves about 95% of my battery capacity always full. So I always have this power stored in my batteries for use, for any time I need to use this inverter. Allowing this to turn on, or turn off, sorry, at 12.4 means that my battery, that my controller was not short cycling the grid tie inverter. It took time to make this 0.2 volt drop before it would turn off, and you had to wait for the power to build back up to the 13.8 where it turned back on, and then it took time to use up that power. So it made a much longer, much smoother cycle for this grid tie inverter. It might take it 5 minutes to use up all that power, and depending on the day, it would take several minutes or more before it reached the 13.8 again, before it would drop and use up that power. So to extend the life of my grid tie inverter, my relays, and this control board that are all turning on and off quickly, I gave up about 5% of my battery capacity. But I am taking all of this and converting it back into 110 and pushing it back to my house. So I'm not really losing this 5% of my battery capacity. I'm just using it currently and not storing it for future use. This way my batteries are full, I'm using the voltage I have, and I'm keeping it from going above a dangerous level in my battery bank, which should make my batteries last for a very long time. I've been running this system for several years, and my batteries are 4, 5, 6, and 7 years old. I bought them 1 year apart as I was slowly expanding this system. So this is how my system is set up. It works very well, and I showed you on the meter earlier, the bottom number at the meter showed how much power I supposedly had saved that was going back into my home power system. So now I'm not only storing solar and wind power, I'm also using it currently while I'm using the grid. Someday I hope to expand the system to the point where my home can be run on it, but at the moment, this is where I'm at. I hope you found this video informative. Down below, I want you to hit the subscribe button, turn on the notifications bell, and then check out our description. This is where you can find our link to join our subscribers email list, and you can find links to many of these components that I used. Do more research on your own and learn more about what you'd be using. Thank you for watching.